Alright, hello everyone, it's October 7th. Alright, I have some new idea of how to do this, so I have to try it. It's different. I'm not going to use binary search because I know the tutorial, at least the method we copy and paste yesterday, was greedy and binary search. But what I'm going to do is greedy, but no binary search. So we'll see. I'm not sure if it's going to work, but I just realized that actually probably is not going to work. You probably have to use binary search. Like, seriously, I think you'll have to use binary search because I just realized, so basically the ideal is we'll keep track of a list of zeros, right? And then when you hit someone that needs to be dried, so you need to find the lake, you need to find the zero that's closest to it, to the right. And I was thinking you can just go from left to right and then ignore all the zeros that has a smaller index than the current one. But I just realized that's not going to work because you can later on hit another thing. So how about, this is, so we get all the zeros, right? And then as we move along, we are going to hit all the others. I don't really think it's probably not possible. Okay, so for one thing, binary search, is it possible to do, let's say, binary search on sorted set? Is this possible? Yes, you can do that. You can do that. Actually, it's not going to be binary search. It's going to be upper bound. Upper bound. Yeah, it can be used on set. So this is what I'm going to do. Upper bound is the smallest that's bigger, right? Upper bound. We can call set.upperBound. The first element that is strictly greater than, so we'll do that and then we'll remove it. I guess that's what we have to do. We have to converge to that. I just realized my other idea does not work. That's fine, that's okay, it's alright, doesn't really matter. Alright, successful pairs of spells and potions. You're given two positive integer arrays, spells and potions of length n and m respectively, where spells I represents the strength of the ith spell, and then potions j represents the strength of the jth potion. You're also given integer success. A spell and a potion pair is considered successful if the product of their strengths is least success. Return an array pairs of length n, where pairs I is the number of potions that will form a successful pair with the I. So basically, it's binary search again. Right, it's binary search again. So basically, for each numbering spell, we need to find how many potions whose product with the spell is larger or equal to success, and that's it. So what we need to do is success divided by spells. So in this case, success is 7, spells is 5, 7 divided by 5 is 1, which means anything larger equal to 2 will work. So I have 1, 2, 3, 4, so I have 4. This requires 7, but we don't have any. And this requires 3, and then we have 3. This is actually very easy. And we're going to do upper bound on this as well. So upper bound finds something that's Interesting. So it says is at least success. So if it's divisible, right? Depends. So we can do, because these are integers, so we can do something a little bit tricky. So if it's not divisible, then we'll do basically this divided by this, right? This divided by this, we'll get the integer portion, and upper bound is strictly greater, right? Upper bound is strictly greater. So upper bound is strictly greater, which means if it's divisible, right? If it's divisible, like in here, 16 divided by 2, it's 8. It's divisible. So if it's divisible, we need to do 8 minus 1. So we need to check the remainder. But that looks easy enough, so we can just go ahead and then implement. Yeah, looks easy enough. Simple binary search will do. So in the sort, potions stop begin, potions stop end. Okay, and then we'll do vector int res spells size. Okay, so for each one, int minimum strength, right, shall equal to success divided by spells. If success mod spells I is equal to 0, main strength minus. So success is but potions are all integer. I guess it's fine. Alright, I guess it's fine. Yeah, no. I think there is a risk. So let's go this long. So now what we need to do is to find, let's say auto it shall equal to upper bound, potions stop begin, potions stop end, and min strength, right? So what we want to find out is, I think I can just say res I shall equal to std distance it and potions.end, and I will return res. Alright, let's just give this a run. Does it work? It looks to be working. Let's try it. Alright, it's working. Yeah, this is pretty simple. Alright, so we're gonna go back to do yesterday's. We will use a sorted set to keep track of the indices of all zeros, right? We also keep track of the indices of all the other lakes. Once a lake need to be dried, we will use greedy to find the closest nearest 0 whose index is bigger, right? Is bigger. If no such 0 can be found, it is not possible. Right. And at the end, if any 0 indices, if any 0 indices have not been used, we will fill it with any lake. So we do need this. I need another map positions, because once it comes in, I need to know which one it is, right? So as we go through, once it becomes 2, I need to know which one's the front. But actually, no, we don't need this, right? We don't need this because at most, I think int is sufficient, right? Int is position, right? So this is the index, right? Index of the undried lake. And we also need std set int. Okay, this is 0 indices. Okay, res, I need res, so I'll go this. If it's equal to 0, then we'll do 0 indices dot add insert I. Okay, else let's just delete all of them. All right, so else. So we'll say if the position contains it, if position dot contains rings I, if it contains, so we need to dry, right? If it contains, then we need to dry. So we know the previous, so int j shall equal to position rings I. Okay, so we now need to binary search in 0 indices dot upper bound j. Okay, so I'm gonna set the auto it equal to this, right? Oh, actually, I'm not sure. Is it iterator? It is. How to delete an element from set using iterator? Erase it. Nice. So right, so this we need to, so if it is equal to 0 indices dot end, we return this, right? So there's no, so this is no 0 is available. Otherwise we have a 0 that's available. So we have it, and I think we dereference it, right? We dereference it, we'll get the value. So now we're gonna say res it is index, so shall equal to range I, right? Shall equal to range I. The j is the position, so this is just, yeah, we'll dry that, and then 0 indices dot erase it, and then position rings I shall equal to I. Right, so we need to draw. If it doesn't contain, it's the first time we just do this. If it contains, then we need to draw. We get J out, we binary search, and if we don't have, if we have, we'll just take it away, and then we'll set its value. Yep. Okay. So then equal to 0. 0 we shall... Wait, when do we do -1? I forgot. -1 if it's larger than 0. Okay, so we'll do -1. So, and then res I shall equal to -1, right? So once we get to the end, so any failure we should be able to identify immediately, right? Any failure we should be able to identify immediately. So when we get to the end, we just need to check if there's any more zeros, right? There's only any more zeros. We can just get a non-zero value, right? We get a position. How to get a key, right? So how to get any key in an unordered map. I don't think they understand my question. Can I pop from an ordered map? Ah, shoot. That's alright. Oh, we just need to do this int lake to no op lake. So we just say for int index of 0 indices res I shall equal to no op lake. Alright, we do have to use this. Alright, let's see. That is very interesting. How come it become -1? Oh, no op. Ooh, this is not right. My bad. So first of all, they should come to the outside. And then no op should come to the outside as well. Because the position, we have to set it anyway. Yep, I think this is the one. Yeah, so I don't think this is any harder. This is not hard. It's just, I don't know, yesterday was a little bit stressed. Was not able to perform very well. Yeah, this type of thing happens. Actually check. Yeah, it should be the same. We want to map a vector, a set, 0 insert, if it contains, well, in the lower bound it's fine, and then we do this, answer this, erase, set it to I, and then boom. Oh, this is actually very smart because you at least have one. Actually, is this allowed? What should this one be? 0, 0, 0. So this should be not allowed. Yeah, we should add a constraint. Either define what will happen, because 0 just means we will have nothing, so I think you should add this. Cannot all be 0. Okay, I actually can. Feedback, restriction, test case missing, runtimes too strict, edge case too frustrating. The constraint should include we should add one more constraint that the rings array cannot all be 0. Currently, a test case such as 0, 0, 0 is allowed, but the official but the answer is 1, 1, 1, which does not make any sense. Right. From the description, a day where rings I equal to 0 on a day we must dry a lake. This suggests that at least one lake must be present. This should be specified in the constraint. Okay, submit. Thank you for your feedback. I actually don't know what's the current I don't know. Where does my feedback go? Basically. I don't know where my feedback goes. To get feedback in real time. Ah, I see. So I send it and it probably will show up here. But that's I don't know. Must be a batch job. Right, it must be a batch job. Well, we can actually check. We'll actually check to see when it will arrive. So we submit at 9 o'clock. So we can see how long it'll take. I'll report back tomorrow. Alright, I'll see you guys tomorrow.